Hello, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Parthe Pandit. He will be speaking on Can kernel machines be a viable alternative to deep neural networks? Professor Parthe Pandit is the Thakur Family Chair Assistant Professor at the Center for Machine Intelligence and Data Science at IIT Bombay. He was a Simons Postdoctoral Fellow at UC Santiago. He obtained his PhD from UCLA and his undergraduate education from IIT Bombay. In 2024, he was awarded the AI2050 Early Career Fellowship by Schmidt Sciences. He has also been the recipient of the 2019 Jack K. Wolf Student Paper Award by the IEEE Information Theory Society. Over to you, Professor.
Thank you so much for the kind introduction. Can everyone online hear me? If not, raise your hand. Okay.
Yes, perfectly audible.
So, hello everyone. Thank you for the invitation to the organizers. How many people here work in machine learning, are familiar with machine learning? Okay, cool. It's okay if you're not. I'll run through some basic stuff. So, I think get started. Okay. So yeah, there has been a lot of like this. There has been a lot of interesting work happening in the space of large-scale data analysis. Data science is now quite popular, and there have been a lot of massive developments over the last decade in the areas of computer vision, NLP, robotics, and what I'm really excited about personally is in the area of in sort of scientific research and how research is done in science today. We are now relying more and more on what are called data-driven models rather than just physics-driven models. And the main reason behind this excitement in this area is this technology called deep learning. There is a lot of cool things happening around us as we speak. But what's a little unsatisfactory from an academic point of view is we lack a satisfactory understanding of this new technology. We don't quite understand them well enough. And I want to maybe focus a few minutes just outlining some limitations of deep neural networks and why I have been thinking about the problem of looking for alternative technologies to deep neural networks. So the first sort of limitation is that predictions that neural networks make are not really interpretable. So if you if a patient goes to a doctor and gets a diagnosis from the doctor that they have a certain disease, they are asked, how did you come to this conclusion? That's a very natural question. And doctors typically have some reasoning as to what they were looking at when they came up with the decision that they made. Unfortunately, we don't quite have a good understanding of how neural networks are actually making the decisions that they do make. They make some predictions. As a whole, these predictions are somehow good based on the generalization error that we define, but we don't quite understand how these decisions are made. And the main reason behind this is that the role of the training data in this entire enterprise is very opaque. We don't know if we were to ask counterfactual questions, if there were a perturbation that is made to the training data, how is that perturbation going to affect the model that I learn at the end of the day? This is the opacity really comes from the fact that the way we train these complex models is non-trivial. We do a lot of things in order to train these models, some of which may not be necessary, and we don't quite have a full grasp on what is necessary really in this space. If you've ever actually taught a course on deep learning or anything related to that, one of the biggest challenges is staying current. Things that people teach in deep learning courses goes obsolete really fast. So there's very limited theory that guides the practice of how deep neural networks are actually applied. There exists some theory, but it's extremely unsatisfactory at this point of time. And the alternative technology that I'm going to spend time today talking about is based on kernel machines or kernel methods as they're called. and they offer a more principled alternative to each of the limitations that we saw on the previous slide. So at a high level, what is a kernel machine? So if these are your training points, the 3 green and the 2 red, and this is the test point, then the decision that you're going to take at this test point about what the function value should be is going to be some sort of a weighted average of how close the weights are dependent on how close this test sample is to all the training points, and you'll take into account this similarity score. So the predictions are based on how similar the test sample is to other inputs in your training data. And the similarity is here measured in terms of what is called a kernel function, and that's what gives this class of methods the name. Right? And here clearly the role of training data is very transparent. So if you were to make any perturbations in the input space, you understand what is going to happen to the test sample, the prediction for the test sample. And what's nice is that the training procedures that you get out of formulating problems in this space are very nice. They're convex optimization problems, and you can actually understand properties and stability of these optimization problems. At the end of the day, you still get a nonlinear model, which is nice because you care about learning some nonlinear relationships between the input and the output without having to deal with the non-convexity. What's the best part is that this is all based on very sort of firmly grounded engineering principles based on linear algebra and probability theory and so on. So you can very nicely teach someone what this is in a couple of weeks, and they'll be up to speed as to what is happening in research in this area. So here's a high-level comparison between deep neural networks and kernel methods. As we saw, the predictions are interpretable, their training procedures are stable, and the role of training data is transparent. But why are these methods not the state of the art before 2012? But now they've sort of fallen by the wayside. And the reason is that their prediction performance is not as good as deep neural networks. And there is some challenges we face in terms of making their training and inference procedures scalable with respect to the size of the data sets. Okay. And my work over the last 3-4 years has been essentially to give some embers of evidence that that we can actually overcome these barriers. Okay, so I'll use this slide to set up the notation also and describe what kernel machines are, and also set up the problem of machine learning more broadly. There'll be some math here. If we have questions, we'll take them right now. So in supervised machine learning, we care about learning a map of the form y is equal to f of x. What you're given is n samples of input-output pairs xi and yi. I'm going to assume that the xi's are d-dimensional real vectors, and yi's are just real valued targets that you want to fit to, right? And the task is to come up with a function f. Kernel machines are a very specific type of function. Okay, so this is the form of the function. So here, this is a linear combination of some basis functions here. K here is the kernel function that measures the similarity that I mentioned before. So here is an example kernel function. This is called the Laplacian kernel function. Okay, so k of xi is e power minus the norm of x minus xi. So as you go further away from xi, the weight of the linear combination drops exponentially. So the weight of xi in this linear combination drops exponentially. Yeah. So you can think of this kxxi as being some kind of local influence of the sample xi, and alpha i's here are my learnable parameters in the model. Once you fix k, you learn the alpha. You can think of the magnitudes of these alphas as being the global influence of the samples. And the way you learn these models is by solving a positive definite linear system of equations. This is an n by n system of equations. K alpha is equal to y. Y is the vector of all the targets. And this K is the n by n matrix, which is formed by evaluating the kernel function at pairs of inputs xi, y, xi, xj. Yeah. Okay. So here is an outline for the rest of the talk. I'm going to spend a fair amount of time trying to understand the gap between kernel machines and neural networks, try to get a handle on this gap, and using some insights that we have about this first part, we'll be able to design a new class of functions, or a new class of kernel functions, which are adaptive in some sense. And these kernel functions perform well. And then I'll maybe spend a few minutes describing some algorithms that we've come up with that allow us to train kernel machines at very large scales of data. Okay. So let's get started. So here is the story so far. When looking at kernel machines and neural networks, these are two different classes of functions, but there exists some equivalence between these two classes of functions. Okay, so infinitely wide neural networks are equivalent to a kernel machine. There is a star there because terms and conditions apply. This equivalence holds under some conditions. So here is the nature of the equivalence. So we are looking at a neural network. W1 is the first layer weights of the neural network. W2 are the second layer weights of the neural network. And I'm looking at the setting where the width of this network is going to infinity. So width is the output dimension of the weight matrix W1. Right? And what I'm saying is that the function is equal to this function, roughly. Right? That is the sense in which they're equivalent. Right? And the equivalence, of course, depends on choosing the right kernel function k. So there exists a kernel function k for which this network is equivalent to this kernel machine. Yeah. Of course, the kernel function that you choose is going to depend on what is the how the network is trained and so on and so forth. Right. So the first such result talks about the setting where you're training only the last layer of the neural network, and that the kernel that arises from that equivalence is what is called the neural network Gaussian process. The exact form of the kernel is not important right now, but there exists such a kernel that makes this equivalence true. Right? This is an old result. This is also not how real neural networks are trained. Real neural networks, you train all the layers that are involved. So Jaco and co-authors in 2018 showed that, well, if you were to train all the layers of the neural network with a small enough learning rate, then the function that you're going to get at the end of the day is a kernel machine. The kernel function corresponding to that is what is called the neural tangent kernel. Again, the form of the kernel function that you get at the end of the day is not too important. Of course, the form of the function that you get will depend on architectural parameters in the network. What is the nonlinearity you're using there? What is the initialization scale of the weights? What is the learning rate that you chose, and so on and so forth. Yeah. What's nice is that these kernels are unsupervised in the sense that the kernel function does not depend on what the targets are that you're trying to fit to. The kernel function is fixed. Right? And these unsupervised kernels actually perform well on many problems. So yeah, what's a little I'll come to this. There exists some other supervised kernels, which is called the after kernel, which is actually great. But that after kernel itself involves training a neural network, and so that's more like a thought experiment. I'll come to that in a bit. Yes. Correct. So the kernel function is unsupervised, is what I'm saying. So the question is, in what sense is this unsupervised? And the answer is the kernel function does not depend on y. The alphas are allowed to depend on y at the end of the day. Yeah. Uh, Not quite. So again, the star hides some more details about how small the learning rate has to be and so on and so forth. So if the learning rate is too big, then this equivalence breaks down somehow. Yeah. I'll get to that again. So radial basis function kernels is what I'll start by. But like these are more generally dot product kernels or something like that. And the question that we now have is, when and why do neural networks actually outperform kernels? Okay, so let's look at a real world example where we see a gap in performance, and let's try to make sense of that gap of performance. right? So here is an example data set which is called SVHN, Street View House Numbers. Okay, somebody went around Pasadena taking a camera and clicking pictures of house numbers, and the task in this particular data set is to identify what is the center digit of the image, right? So for this image, the center digit is 1. This image, the center digit is 3. Here, the center digit is 6. Yeah, there is some information outside the central part of the image, but that is sort of not relevant for this particular task at hand. Yeah. So this is typically the signature of problems where you see a gap in performance, when only a part of the input is actually relevant to the task. The rest is noise as far as the task is concerned. Right? So if I were to train a Laplacian kernel model, right? This is a data set which has 58,000 samples. If I were to train a Laplacian kernel model, I get a 75% accuracy. If I were to train a deep fully connected network, I get an 85% accuracy. This is a 10% gap, which is big enough for you to not use kernel at all. Okay? Yeah, so why does this gap exist? The folklore around this has been this notion of feature learning, and we'll try to get a handle on what exactly feature learning means. We'll try to make this a little more mathematically precise, right? And in order to do that, I want to work with a slightly simpler setting that allows me to play with this and make this gap a little more stark, right? So here is the setting. My xi's are 100-dimensional Gaussian vectors. Okay, so D100. Yi's are some function of xi, and the choice of function I'm taking here is the product of the first and second coordinate of the input. Right? The yi's don't depend on the remaining 98 coordinates of the input. The 98 coordinates of the input are noise for this problem as far as we are concerned. Right? And now I'm going to do this particular thing, which is I'll only train the first layer weights of a 2-layer ReLU. Okay? The simplest that you can think of. Simplest non-network you can think of, right? If I were to train over 1,000 samples, okay, I get consistently over 80% accuracy for the neural network, right? And I get consistently less than 20% accuracy for the Laplacian kernel model. So this is a bigger gap that I've managed to create. And the only thing I'm training in this is W1. Okay, so something special is happening in W1, and we want to understand this a little better. Okay, so what is happening inside the trained network? Okay, so once you're training this W1, something special seems to be happening. Let's look at what's happening inside the network. Okay. Before doing that, if I were to make this one intervention, which is I just zero out the parts of the input which I'm feeding into my training procedure. Okay, I zero out the parts which are actually irrelevant to the problem. So the 98 coordinates, I just zero them out. If I do that, both of them are going to perform really well. Both of them give me 95% accuracy consistently. Okay, so what's happening is that the neural network, the first layer weights of the neural network are sort of doing this for the network of this task of zeroing out parts of the input somehow, and we'll see how that actually is happening. Okay. Now, zeroing out is the same as the notion of rejection, and mathematically rejection is best captured in the null space of this weight matrix W1. Null space of W1 is the same as the null space of W1 transpose W1. Why I want to work with W1 transpose W1 is because this is a D by D matrix. This is now independent of the width of the network. Right? So I want to visualize what is the null space. So this is the plot of what W1 transpose W1 looks like. This matrix is very sparse. It has a very few non-zero entries. Okay. And if you actually zoom in, the only two big entries that pop out in this matrix are the top two entries along the diagonal. Right. So now every time you take a new input X and you pass it through the network, what does it do? It just zeroes out everything that's not in the first two coordinates. Right. That's what W1 is doing in the first layer. Right. So this is a visualization of what happened after the network was trained. Right? You'll see this matrix W1 transpose W1 come again and again. I'm going to call this the feature matrix. It will become a little apparent why. So yeah, if I were to now look at what is the so the top right singular vector of W1, which is the top eigenvector of W1 transpose W1. Okay, this is a d-dimensional vector, which is the same as the dimension of the input. So I can represent it exactly like the input is. Okay. So when I visualize that for the SVHN dataset, what pops out is this kind of a pattern. Okay. What does this pattern mean? There is information in the middle part and no information in the parts that are not in the center. Right? So anytime a new input is hit with the first layer weights of the matrix, all perturbations that are orthogonal to this pattern die out, and everything that is along this pattern stays. Right? So everything that is in the center stays, everything else in the input gets attenuated. Right? So that is why we call it the feature matrix. The eigenvectors of this matrix you can interpret as the features of the learned network. Okay, so let's look at some more features that are learned by the neural network. So this is the Celeb A dataset. So these are high resolution images of celebrities in the US. So mostly white celebrities. There are several binary classification tasks associated with this dataset. Okay, so the inputs are the same, but the targets that you want to fit are different. Okay, so these are 4 different binary classification tasks. Whether or not the celebrity has a 5 o'clock shadow, which is a certain type of beard, whether or not they're wearing a necktie, whether or not they're smiling, whether or not their cheeks are rosy, right? I trained 4 different neural networks, okay, and I look at what is the top eigenvector of W1 transpose W1 for each of these 4 neural networks, okay, and what pops out is information that is related to the task that we're trying to capture. Right? So for example, in the smiling prediction task, you see a smile show up in the top feature. So all patterns that are not like this will get attenuated. All inputs that are not like this get attenuated. Similarly, in the rosy cheeks, you see rosy cheeks show up. All patterns that are not like this are going to get attenuated. Right? So the first layer weight matrix for these target specific patterns in the input. How can we codify this a little more precisely using some math, right? And so here need to define another mathematical object. We are not the first ones to actually define this. This was defined a long time ago by Hardle and Stoker in 1989. And the context in which they were studying this object was to find subspaces relevant to a target function. Okay, so something very similar. What is the correct subspace related to a given target function? So the name of the object is expected gradient outer product, and it's best defined using an example. Okay, so if you were to take a function, let's say f star of x is x1, x2, where x is some 100-dimensional Gaussian. The gradient of f star with respect to x is x2 in the first coordinate, x1 in the second coordinate, and 0 everywhere else. This is just a quadratic function. Right? Now the expected gradient outer product is you take the gradient function, you take the outer product of the gradient function, right? So this is a rank 1 function. This is a d by d matrix, and then you take an expectation of this d by d rank 1 function. Right? So that's a potentially full rank matrix. And for this particular example, this is going to look like this. It's a 100 by 100 matrix where it's only 1 in the first 2 coordinates in the diagonal, 0 everywhere else. Right? And that is what we're calling the expected gradient outer product. Okay. What does it do as soon as I hit a new input with the EGOP? It zeroes out everything that's irrelevant to this particular target function. Right? So this is sort of the correct object to be looking at, to be doing the target specific dimensionality reduction that you want to be doing. Right? So this was studied in many different contexts before us, such as multi-index models, metric learning, structure adaptive dimensionality reduction. But we are the first ones to make a connection to feature learning in neural networks. And this is what we propose or posit as the mechanism by which feature learning is happening in fully connected networks. Okay, so we call this the neural feature ansatz. On the left hand side is the feature matrix of a trained neural network, W1 transpose W1, D by D dimensional matrix. On the right side is an empirical version of the EGOP, which is the average gradient outer product, AGOP, right? And so if G is the network function and W1 are the weights of that network, we're looking at the average gradient outer product of the network function, right? And this is, we're saying that these two objects are close to each other after the training is done. Any questions? Okay, important thing to notice here is that these are gradients with respect to X. Okay, so here is some evidence that this actually is happening. So if you were to visualize the top eigenvector of the AGOP of the entire network function, right? So the network function, you can take the gradient of the network function using some backprop or even potentially finite differences, and you look at the top eigenvector of that AGOP, and you see exactly the same patterns pop out in both of them. Yeah. I mean, maybe this task it appears that the first layer seems to be doing a lot of the heavy lifting. Another thing to note is that, well, during training, W1 is now dependent on all the other weights also. So this is after training. So W1 contains information that is related to the other network. Correct. Correct. Yeah. So you're training using some other technology entirely. You're using gradient descent in some parameter space. That is a different gradient. But that gradient essentially allows W1 to bake in information that is related to the other weights also. So W1 is not really independent of the other weights in the network. Okay. Yeah, so there's a very high correlation between both the objects, W1 transpose W1 and the AGOP of the network function. So these are just correlation between two D by D dimensional matrices, and there is a very high correlation between them. So AGOP is this, so the averaged version of the expected gradient outer product. Yeah. No, this is for, the ansatz is for any depth fully connected network. For now. I'll describe what happens in other networks a little later, but for now, this is for fully connected networks. Yeah. Yeah, what happens in the other layers of the network? So something very similar seems to be happening in the other layers of the network. So you can think of the intermediate layer WL by decomposing the network a little. So G is still the entire network function from input to output. Okay. I'm going to call small hl as this subnetwork before the LH layer weights, and capital HL as the network subnetwork from this activation till the end, right? So WL transpose WL is DL by DL, where DL is the dimension of this activation, right? And that is the average gradient outer product of this subnetwork. But the average now is with respect to the distribution, that is the push forward of the input data through HL. This is the deep neural feature ansatz. Okay. And I is my training data. So Xi are my training data. And I don't have actual access to the entire distribution. So yeah. So here is some more evidence that these two objects are actually very similar to each other. This is still just empirical evidence, but at initialization, these two objects are very different from each other. So these are I'm looking at the correlation between this object and this object averaged over 121 different networks, trained over 121 different data sets. Okay. And at initialization, their correlations are very low, but somehow through training, their correlations increase significantly. So greens means after training, the correlation after training. Reds are correlations before training. No, so actually the variance in layer 1 here is showing because the 121 data sets have different dimensionalities, and so but it's still like really, I mean, half correlation is not really significant correlation. Yeah, if we had normalized it a little differently, the initializations of the weights in the first layer a little differently, you would have again seen. Okay, so so far this is our description of what is happening in each of the layers of the neural network, and now we'll use this insight to design a new family of kernels. Any questions so far? Okay, so here is how I think of this deep network. There is a weight matrix. There are more layers on top. Okay, the new kernel that I want to propose is something like that. I take my old kernel model and I prepend it with a weight matrix, let's say W1. Okay. If I was using the Laplacian kernel, this is what this means. The function is now sum of alpha I k w1x w1xi. Yeah. And because of the special structure of the kernel, the Euclidean norm has now become a Mahalanobis norm, which weights the different dimensions differently. And the object that comes out is W1 transpose W1 again. Right? Now, in the beginning of the deep network, what ended up happening was W1 transpose W1 was the average gradient outer product of the network that I trained. Right? I'm going to choose W1 such that it's going to be target adaptive based on this sort of ansatz as the inspiration. I'd like the final end-to-end function to have this property that W1 transpose W1 is the average gradient outer product of the function f. Right? In the neural network training, I was training W1 and G simultaneously because that was using some other technology. But there is no reason to believe that I need to do that simultaneously in this case. So what I'll do here is that learn f first by fitting a linear system of equations to find alpha. Okay. Once I find alpha, I will set W1 transpose W1 by enforcing this condition. Okay. So here is the scheme that we get at the end of this. We call this the recursive feature machine, RFM. So we start with, so instead of working with W1 transpose W1, we just reparameterize W1 transpose W1 to M. Okay. And we'll work with M. M is a positive definite parameter. And we'll initialize that M as the identity matrix. Okay. So this is now a parametric kernel, which has the Mahalanobis norm in the exponent. Right. So the step one is to fit a predictor, which is find alpha I for a given M. This is solving a linear system of equations. Yeah. Why does this? Why did I choose this? Yeah, so it turns out there is a good reason to choose this and not the Gaussian, for example, which is these functions are equivalent to the neural tangent kernel functions, which are equivalent to neural networks trained with a small learning rate. So that's the sort of they're as expressive as deep neural networks with a small learning rate. That's the reason to start that. Yeah. So yeah. So here I'm again using the Laplacian kernel, but you could do this with any other kernel. That's also fine. Okay, so we fit alpha I, and once we fit alpha I, I'm going to just set M is equal to the average gradient outer product of F that I got from step one, right? Which is nothing but you calculate the gradient of F with respect to the inputs. These are well-defined objects. and then you take the outer product and just sum over all the training data, right? And you just recurse over this a few times. Okay. What happens at the end of this is, so I'm showing you the top eigenvector of M that I get after training this recursive feature machine, RFM. Okay. And these are the eigenvectors of the first matrix of a neural network. What's interesting is that these features were obtained without ever involving a neural network at all. So I now have the ability to train functions that learn neural network features without actually ever involving a neural network. Yeah. What's also interesting is that the RFM has a better test accuracy than the neural network that you began with. So this is a better predictor overall. Yeah. Okay. This was just for sort of one celeb A data set. We've sort of stress tested this method on a wide variety of data sets. So this is a benchmark from 2014 that compares 179 methods on 121 different data sets, which have small data, which is as small as 500 samples, to large data, which is medium data, which is up to 130,000 samples. It's not large by today's standards. And RFM actually comes out on top over all the 179 methods. There are several other metrics that we compare, but it comes out on top on all the metrics, not just these two. What's also interesting is that RFM takes only 40 minutes to train on this particular benchmark. Neural networks take an order of magnitude more time. Yeah. Because training a neural network means you have to tune a lot of hyperparameters and all that. Sorry? Not really, no. Yeah, that's not too expensive. And you can sort of you can just embarrassingly parallelize these because it's just a linear combination. If you have 10 GPUs, you can cut time by a factor of 10. Yeah, this is training time. He's asking about inference time. Yeah. This is only training. This is training time. This is not inference time. We also now have ways to do fast training. So this is still using the simplest training, which is you invert a matrix of 130,000 by 130,000 brute force. The only hyperparameter we have to tune is how many iterations you actually take for this recursive feature machine. In practice, we only do up to 5 recursions. We don't even do more than 5 recursions. Okay, this was a slightly older benchmark. There is a newer benchmark with newer models. So 2022, this benchmark has fewer data sets, but each data set is much bigger. And again, there are more recent models like XGBoost, boosting trees, ResNets, MLPs, and transformers, and so on and so forth. RFM again comes out on top on all the metrics that we work with. Yeah, so RFMs actually outperform XGBoost, which is the thing people use in practice in industry for analyzing tabular data sets. And again, what's interesting is RFM takes about an order of magnitude less time than XGBoost does. Again, because there is only one hyperparameter tune, which is how many iterations you want to do. No, we did this. We have, yeah, we had a GPU grant that allowed us to burn some trees. Yeah, but like we actually ran this. We didn't run these numbers. These numbers are run by industry. Yeah. Yeah, so going back to the data set we started with, which was Street View house numbers. If you look at what are the learned features by the deep network and by RFM, both of them have now identified that, well, you have to look only at the central part of the image and not outside that central part. Once you do that, you basically bridge the gap to deep neural networks. Yeah, the 10% gap is gone away. Okay, there are many other deep learning related phenomena where RFMs are. So RFM is sort of now an alternative to do deep learning entirely. What I showed you was only for fully connected networks. We have a more verbose paper that talks about how to do this for convolutional networks, how to do it for RNNs, how to do it for transformer networks, and so on and so forth as well. But it also exhibits many of the properties that are present in deep neural networks. So a lot of the issues that exist in deep learning also exist in RFM. So one such issue is what is called the simplicity bias. So here is the setting in simplicity bias. What is done is you take two data sets. CIFAR10 is one data set. MNIST is another data set. So CIFAR10 has sort of natural images. MNIST has images of handwritten digits. Okay? And then you just mash these two data together. Okay? But you mash them in a manner such that each class corresponds to exactly one class from the other data set. So the 0 comes with airplanes, the 5 comes with dogs, the 7 comes with the horse, 9 comes with truck, and so on. So there are 10 pairs of classes now. You train a neural network. The neural network learns to entirely ignore what is happening in the CIFAR10 part of the input, because the CIFAR10 dataset is a hard dataset. We don't have good prediction accuracy using just simple models on this dataset, whereas MNIST is a simple dataset. And so the neural network, because it can predict the correct pair of the class, just by looking at the CIFAR, the MNIST part of the image, it entirely ignores what is in the CIFAR10 part of the image. This is called simplicity bias. Okay? Turns out RFM does exactly the same thing. So it learns this. You don't actually need information in the CIFAR10 part of the image to predict the correct pair of class. Okay? This can also be a bad thing because okay. This can also be a bad thing because you could potentially have spurious features also, right? Dogs are typically models learn wrong patterns in the data rather than the actual thing that they should be looking at, right? And so we now have a sort of analytically simpler model that can exhibit many of the mystical phenomena in deep neural networks. So here is a list of such complex deep learning phenomena which are exhibited by RFM. We have some follow-up papers. The spurious features setting is talked about in the original paper by Radhakrishnan and co-authors. Adversarial examples are also shown in the same. We can actually get an understanding of what exactly are adversarial examples, how you can create adversarial examples also just by taking advantage of the ansatz. And there's also a new set of phenomena that has come about in the land of large language models called emergence or grokking. Okay. This phenomena was believed to be sort of specific to neural networks, but we show that no, RFMs also exhibit this same phenomena. Okay. So from a theoretical point of view, there's some hope now because RFM essentially is a much simpler model in some sense that exhibits the same properties of deep neural networks. So you can better analyze this model than analyzing deep neural networks, which are much more complicated to analyze. Okay, so let me describe some algorithms that allow me to train these kernel machines at very large scales where the number of samples is very high. Okay. So one first simplification that I'm going to do, which is practically very useful, which is the following. So in the original kernel machine that I showed, I was taking a linear combination of n kernel functions. Right? Instead, you can maybe choose only p centered kernel functions. Okay? So the basis functions that I'm choosing, I'm going to reduce from n to p. Which means that every time I want to make an inference, my time has gone down from O of n to O of p. Right? And p can be much smaller than n. So there are different ways in which you can choose these centers. You can do something like just subsampling. You can do k-means first and then do subsampling based on k-means. I'm going to focus on the setting where somebody has given me those centers. Okay? and I just want to find the coefficients alpha I. So I now want to find P coefficients alpha I. Okay. So that is the setting I'm going to study. What's also nice now is that I can train a kernel machine on a data set of any size. N can be as large as you want. It can be a billion, that's fine. Right? Yeah. So there is a limitation to this approach. Okay. What is the limitation? The performance actually saturates as you get more and more data. Right. So what I'm showing you here is the performance of the Laplacian kernel on ImageNet. And on the x-axis, I'm increasing the size of the training set, and on the y-axis, I'm showing you what is the accuracy. The model that I'm choosing is this model with p center. Right? So P is what corresponds to the legend here. Right? So as you increase the size of the training set, your performance increases, but then it saturates at some point. Okay. So what you do, you increase the so this same phenomenon happens in deep neural networks as well, which is why we just increase the size of the model, and that's why we have these very large models that we work with today. Increasing the size of the model increases the performance. And so when you do that in this context, which is increasing the number of centers, you see a bump in performance. And now the point of saturation shifts to the right. So you saturate, but you saturate a little later. Right? And then you can keep doing this. You can keep increasing the size of the model. You will get better and better performance. The question is, does this actually scale? Like, can I keep increasing the size of the model indefinitely? So here is what the state of the art was before our work came out. So this algorithm is called a Falcon algorithm. This is the performance of Falcon on the Libri speech dataset, where n is 5 million. And on the x-axis, I'm now varying the size of the model, which is the number of centers in my model. So I keep increasing the size, the test accuracy keeps improving, but suddenly I run out of memory. Okay. When I inspect what happened, the algorithm was trying to allocate a terabyte of RAM to train a model of size 512,000 centers. Okay. I somehow found a way to get a machine with 1 terabyte of RAM. I was able to make it work, but then when I tried to train a model twice the size, I needed 4 terabytes of RAM. So essentially, Falcon requires quadratic amounts of memory for training a model with P centers, right? And our contribution was coming up with a new training algorithm which requires only linear amounts of memory. Okay? And this algorithm, which we call EigenPro3, essentially allows you to keep increasing the model size indefinitely. Okay, so the first paper came out in ICML 2023. So that required still quadratic number of flops per sample processed, which is non-ideal, but it was still able to do this in linear amounts of memory, which is nice. But this is not nice, and so we had to fix this. So we came up with a follow-up paper which allowed us to do this in linear amount of time as well. This new algorithm, which we call EigenPro4, is suitable for any kernel, any choice of centers, any number of samples. So you can, this is a really flexible algorithm, and it's delightfully parallel. If you have 8 GPUs, you can cut down time by 1/8. And it's also resource efficient, which is that it utilizes all the GPUs fully. This is not something you can do in deep network training. You can't fully utilize the GPU because if you keep increasing the batch size, you need to, the number of epochs that you need to train for increases. And so the optimal batch size at which you train a deep network is typically only utilizing deep networks, the GPU memory up to maybe 20-25%. So here is a quick table that shows some numbers. So as I go below, I'm increasing the size of the model that I'm training. Okay. This is on a variety of different data sets. 5 million samples, 6 million samples, 10 million samples. There's also a version with 16 million samples, but I don't know. I think this might be a typo here. Okay, so Falcon goes out of memory for all of these because you need 4 terabytes of RAM for training a 1 million center model. EigenPro 3 would take up to 20 days to train this model because it was a model designed, it was a algorithm designed to work with limited memory, but wasn't really optimized to flops per sample. And once we fix that, you get about a 400 times speed up. You can train a model with 1 million centers in about an hour. Yeah. So there is one thing that is very commonly done in machine learning today, which is data augmentation. You keep adding more and more perturbations of the input as data. Okay. You keep the output the same, but you keep perturbing the input. That's what they call data augmentation. And that typically always increases the performance of the model. We can do that very nicely now with these EigenPro algorithms, and we typically always see an increase in performance. These kind of interventions which increase the size of the data set were previously inaccessible to kernel machines, but they have now become accessible thanks to our algorithm. Okay, so I'll conclude with a summary. So what I started was with an ansatz for what is feature learning in neural networks. And this ansatz suggests how we can design a new family of high quality kernels. And these kernels can be trained with fast and scalable algorithms that I showcased. And so I want to end with the question, are kernel machines all we need?
Thank you, Professor, for an informative talk. Any questions from our audience?
I think the question is the function we work with is from RD to R. Does it work if I want to do multi-output functions, if I want to learn multi-output functions? So multi-output functions with kernels is non-trivial. That's still one open problem to figure out. I mean, you can do it. There is a naive way of doing it. You just pay a price multiplicative in the number of outputs that you have. This doesn't scale well if the number of outputs is like large language models, which is 50,000. That's typically the vocabulary size. The ansatz that I presented also still holds in the multi-output setting. So the weight matrices still satisfy the same ansatz when your networks are multi-output networks. Instead of looking at average gradient outer products, you look at average Jacobian outer products. And those are still well-defined objects, and the ansatz still holds with high fidelity. Yeah.
You say that RFM outperforms the neural network and the XGBoost. So here it is written fast and scalable algorithms too. So RFM generally doesn't scale if my data set is large enough because it has a tree-like approach. So complexity generally increases, right?
I don't see the tree like, no, it's not. I mean, you just have to fit a kernel machine. So if you use the EigenPro algorithms, you can fit these kernel machines quite fast.
Okay, so if I have my data set to be large enough.
Right. So this is a sort of 10 million size data set. It's taking an hour. If you and the scaling is linear in the size of the data set.
I see.
Yeah.
Right now, these are all gone for kernel machine training.
Right.
So deep neural network might actually get way much.
Right. I mean, the comparison is a little unfair in some sense because deep networks have had like 10 years of engineering to sort of optimize every single thing that has to do with sort of timing information. So the comparison is not quite fair. But yeah, like deep networks also take this order of magnitude time. I mean, it takes about, yeah.
You're not doing better than that time, but it's just because
Yeah, so like it depends on what network you are training, and typically in deep learning you can't just train one network and get away with it. If you want the best performance, you have to tune a lot of hyperparameters. So that's that is also time you should take into account.
right. So
Yeah.
doing that as well, because you have only one asset parameter, they are separate.
Right.
So in the neural feature ansatz,
Uh-huh.
you work with the features after L layers.
Uh-huh.
Now in FID, you would take the inception net and like take features after a certain number of layers. I'm wondering for vision-based tasks,
Uh-huh.
if there are these pre-trained networks that you can use to extract the features for you, and then use those as the things that get fed into the kernel.
Yeah. So in these numbers also, right? Like this is CFAR 10 with a star and CFAR without star. The star is actually the setting where you actually take some pre-trained features and then train a kernel on top of that. That works better because, of course, the pre-trained features are typically better. Yeah.
Sorry, there's another question. In the algorithm where you're alternatively learning you're solving the linear system and you're also learning in that, what if you do it naively and just backprop through both um, the kernels, you're solving the linear system, and so you don't do it alternatively, you do it all at once.
Yeah, it works well.
Would that be better than
You have to tune some things. There is numerical instability. You run into some of those issues. People have done that and it works really well. I mean, yeah, people have done that and it works really well. You learn the same features again, but then it's not a convex problem anymore. So whereas here it's sort of a sequentially convex problem, and that's why it's somewhat attractive.
So in your algorithm, whatever you just took the first set of weights, right, and then you just start a machine. But you showed that the answer worked every layer. But what was the point? Did you use it?
So fully connected. So there is a version called Deep RFM where we can introduce these M's, one for each layer. For comparison with fully connected networks, it never helps to have deep feature learning sort of. So one potential is inference you could draw is that depth doesn't matter too much in fully connected networks. But as soon as you go from fully connected networks to convolutional networks, there is a version of RFM which we call convolutional RFM, where again you have a similar kind of structure. There, training like multiple M matrices helps. Yeah. So the ansatz actually ends up being useful for the later layers as well. I didn't show those results today.
Thank you everyone for attending. We have arranged refreshments in the coffee hut. Please continue your conversations there. Thank you.